Hello, everyone. So welcome to the number 47th Open Seminar in Frontier of Nuclear Physics. And the seminar is held by the Institute of Modern Physics, so the Key Lab of Nuclear Physics and Ion Beam Application, Fudan University. And the seminar is also sponsored by the Program of Introducing Talents of Discipline to University and the Journal of Nuclear Science and Techniques. It's also, the seminar is live streamed on the website co-share.com. So today it's our great pleasure to have the speaker, Professor Adam Kisiel, who is a professor at Warsaw University of Technique. So now I very briefly introduce about him. He received the PhD in physics from the WUT in 2004, and then carried out researches at Ohio State and at CERN, participating in the Rick Star and LHC Alice experiments. He took the current professorship since 2012. So Adam served as a spokesperson of the NICA MPD experiment during the 2019 to 2021. And because China, we also have a few institutes and colleagues join the MPD. So for those of you must already know Adam. And Adam also served as the deputy director of the high energy physics lab at GINR during the past 2 years. So he's one of the pioneers for the study of the momentum correlation in heavy-ion field. He has published many collaboration papers, supervised more than 10 PhD students, and also received a few awards, like from the Prime Minister of Poland and the National Education Commission. So today he will talk about some experimental topic related to the ALICE and in relativistic heavy-ion collisions. So let's welcome Adam. Thank you.
So thank you very much. So let me show myself, but when I will be showing my slides, I will not be showing my camera. So today I would like to talk to you about a connection between astrophysical phenomena, neutron stars and their interactions, and heavy ion collisions. And so I would like to thank the organizers for giving me the opportunity to talk to you about this topic. And this is also more or less my work in the last several years. So as we all know, the main goal of the heavy ion collisions is the exploration of the QCD phase diagram. But this phase diagram is also probed by various astrophysical phenomena, and depending on the collision energy of heavy ion collisions, we probe slightly different areas of this diagram. For example, the LHC usually probes this diagram in the region of very, very low biochemical potential and extreme temperatures. This is where the early universe is believed to actually be placed. But if we go with energies to lower values, we actually explore higher biochemical potential and slightly lower temperatures. And that actually happens to be the region of the phase space that is also probed by such astrophysical objects like neutron stars or supernova, or more recently, extremely interesting neutron star mergers. And especially these compact stellar objects are, first of all, extremely interesting, but second of all, not really that known. And there is, for example, still an ongoing debate whether a neutron star is composed purely of neutrons, of nuclear matter, or actually there are some theories proposing that it might contain some degree of quark matter. And even if we agree on the, let's say, more traditional or normal composition of neutron stars, basically composed of regular nuclear matter, there are still some open questions really unresolved up to today. What is the composition of these neutron stars at the very core, especially when the density is highest? And for example, there are very interesting questions about the appearance of strangeness in such objects. This equation of state of nuclear matter is, of course, probed and one of the main interests of nuclear physics. However, obviously, we in the laboratory have access only to symmetric nuclear matter, where neutrons and protons are appearing in equal numbers. However, in neutron stars, we actually believe that the matter is neutron dominated, and that makes the predictions about the behavior of such equation of state a bit more difficult. And even more, if we actually believe, and there are some strong reasons to actually believe that it might be true, that in this neutron matter strangeness appears, then the equation of state can even be modified further. So these are all questions that we would like to establish using all the experimental information that we have at hand. And one of the important new pieces of information that we should be getting very soon is the information about the actual size of the neutron stars. For example, it is predicted that quark stars will be slightly smaller than the actual neutron stars made of actual neutron matter. And there is a specific experiment, a NICER mission on ISS, which is supposed to measure the actual size of the neutron star. And this is extremely interesting because this actually utilizes the gravitational bending of signals from the hotspots on rotating neutron stars, and they are actually bent by gravity. The gravity is so strongly distorting the space-time at the vicinity of neutron stars that actually the hotspots that are pointing away from Earth are actually their signals are bent by gravity to actually arrive at in our direction. That very significantly modifies the oscillations of the signals that we see from neutron stars, and by the strength of this modification, we can actually deduce directly the size of neutron star, which is, I think, quite remarkable if we remember that the neutron star is about 10 kilometers in size. But of course, the other extremely exciting way to probe neutron stars that has been recently used or become available is the observation of gravitational waves. As I hope you know, the LIGO and Virgo observatories of gravitational waves have been very recently, basically last 5 years, finally successful in observing gravitational waves. And the first signal that was observed by these laboratories were actually gravitational waves caused by the mergers of black holes. That is in itself an extremely interesting phenomena. The confirmation that we are actually able to observe gravitational waves is a fantastic achievement. You can see here that the signal for such a extremely violent and energetic event in the cosmos takes about a fraction of a second. And what we observe are actually changing frequency of gravitational waves that are observed in the LIGO and Virgo observatories. But for us, maybe even more exciting and extremely useful turned out to be the observation not of merger of two black holes, but the actual merger of two neutron stars. And this is a signal from such observation, which actually came very, very soon after the observation of first gravitational waves. And this is the observation of two neutron stars merging. This is slightly different from merging of black holes in a sense that it lasts a bit longer. If you see on the time scale, it's actually tens of seconds, not a fraction of a single second. But this observation is, of course, extremely interesting because, first of all, it gives us the gravitational waves for two neutron stars. And the peculiarities of the oscillations are actually directly related to properties of the equation of state of such neutron stars. And second of all, this particular merger of two neutron stars, we were extremely lucky to actually observe simultaneously in electromagnetic spectrum, which was a bit of stroke of luck, but also turned out to be extremely productive in scientific outputs. But from what is interesting from our point of view is that first of all, we are actually observing mergers of neutron stars. So we are actually probing the properties of neutron stars as opposed to black holes. And second of all, usually the merger of two always the merger of two black holes results in a black hole. In other words, while when this sort of stops, this gravitational wave signal is after the merger is very much difficult to observe, while for neutron stars, we can actually observe not only the signal before the merger, but also the signal after the merger, although the current observatories are still not yet able to distinguish this, but the planned in the near future observatories would be able to measure that. And we already have a very vibrant theoretical community that is trying to model the oscillations that we observe in such mergers and actually relate those oscillations to the structure of the neutron star. And in particular, here at the lower plot, you see an example of such calculations where there were two hypotheses about the structure of neutron star. In one, quarks are actually deconfined in the center of the neutron star, and the other one, they are not. And as you can see, we actually see observable differences between the behavior of this gravitational wave signal from such two scenarios. In other words, we hope that in the near future, because of the rapid development of gravitational wave observatories, we would be able to actually probe this kind of questions just by observing gravitational waves, and then hopefully also the electromagnetic signal from such mergers. So of course, the merger of black holes does not produce any observable signal, it's just gravitational waves. And so here are some examples of such calculations, theoretical calculations of what happens when two neutron stars merge. And you can see here the density of the system as a color scale, and then you can also see time scales, and you can see this is in milliseconds. In particular, this is a specific simulation which actually shows that it's entirely possible that in the center of such neutron star, phase transition begins to deconfine quark matter, and in the final result of such simulation is that the quark matter is actually present at the center of the neutron star. So these are questions which are very, very similar to the questions that we are asking in heavy ion collisions. So we might say, well, how can we, I mean, what's the, let's say, main point of interest in the neutron star studies? And this is, in fact, its equation of state. The equation of state of the neutron star is what determines its properties, and in particular, here on the lower left panel, you can see simulations of neutron stars or possible parameters of neutron star which are allowed by a specific proposition of the equation of state. And you can see there are many, many proposals for different types of equation of states, and they are plotted in the phase space which is sort of natural for neutron stars, a mass of a neutron star versus its radius. And you can see that several equation of state allow or not allow specific combinations of masses and radii. And up to recently, we were only able to measure the masses, and actually the measurement of the heaviest neutron stars proposed already quite significant constraint on which equation of state are actually allowed. But now we will actually have a second line here, the vertical line from NICER mission, which will be able to actually measure the real radius of a neutron star. So that should allow us to even more study what is happening in this equation of state. However, as you can see in the upper right corner, there is still this debate on whether inside the neutron star some strange matter occurs, and that turns out to be quite significantly influencing what is the equation of state of neutron matter in a neutron star. But there is a small complication here when we're talking about the appearance of strangeness in the neutron matter, in which that if we just put strange particles, in particular lambdas inside this matter, it makes the equation of state a bit more soft. That is in a rather large tension with the already observed masses of neutron stars. So such equation of state have difficulty explaining such large masses. However, there is a very much unresolved question of what would be the interaction of these lambda hyperons with the neutrons around them. And this is very much not measured. So there is an open question, and potential interactions or strong interaction of lambdas and neutrons, two particle or even many particle interactions, could potentially alter also the equation of state. So it's not just the appearance of strangeness, but also how the strangeness interacts with regular matter that determines our equation of state. So we actually try to ask very similar questions when we're looking at heavy ion collisions. In heavy ion collisions, we actually proceed through several stages. So especially in collisions on the scale of GeV and higher, we are expecting that these nuclei that collide actually at the very beginning produce a very much unequilibrium state. But very quickly, especially in higher energies, it's basically proven that deconfined quark-gluon plasma is created. And this deconfined plasma is, of course, already at the very beginning starting producing observables, penetrating observers such as photons, electrons, and very heavy energetic particles, jets, which then fragment into showers of particles. But then the system, of course, very rapidly expands and by result also cools. And in the end, we have hadrons, which then interact and finally arrive at our detectors. But if you look at the hadrons that are produced in such collisions, you actually see that there is quite a lot of baryons, including, of course, a lot of strange baryons, which, when they actually are created, they interact, and there is a separate technique that is used to actually measure the interactions of those baryons in the final state, and that allows us to actually probe the interaction of baryons, which is not really accessible in any other way in the experiment. So in such collisions, you can ask what is the baryon density and the energy density that is reached. And here you can see at fair and RIC energies, of course, a very much lower end of RIC energies or the fair energies. You actually, if we are talking about collider collisions of 3+3 or 4+4, or solids or target collisions, stationary target collisions of 50, 20, 30 GeV per nucleon, we actually observe that the net baryon density in such collisions, which is reached in these collisions, is actually maximum. When we want to see which experimental facilities are actually able to access this region, you actually see that this is beam energy scan of star, and they actually reached this region and it extended it with this star program. Of course, the fact is that star beam energy scan data taking is finished. This program is finished now. Star is still taking some data, but very soon it will be shut down in preparation for the construction of ERIC. Then we have NICA and MPD, which sits right in the range where this all these things are happening. And then we also have future planned facilities such as CBM, FAIR, and also HIAF. So we are very much right now actually coming back to this energy range and studying anew with new detectors, new luminosities, new large samples of data. And in such a collision, especially at slightly higher energies, we actually understand that this collision undergoes a QGP phase at the beginning. Then there are large pressure gradients producing very strong flows. These flows are actually one of the observables that are telling us something about the equation of state and how this matter behaves. And then this matter again expands, cools, hadronizes, and what we observe in the detector are actually individual hadrons and particle spectra and many other correlations that can be done with such particles. But what's extremely interesting, I think, and very, very nice is this kind of simulations which are showing side by side. And let me just bring your attention to the left plot when on the upper side you have neutron star plus neutron star. On the right-hand side, you have gold nucleus and gold nucleus. Note the change in scale. On the left, the scale is in kilometers. On the right, the scale is in femtometers. It's 18 orders of magnitude difference. But the scale on the z-axis or the color axis is actually the same. This is the temperature of nuclear matter. So it's I think, extremely remarkable that we are comparing objects that are 18 orders of magnitude difference in size, but we are sitting in exactly the same spot in terms of temperature. So we are truly probing in laboratory, in heavy ion collisions, the same matter as we are probing in neutron stars. So, of course, the advantage of having it in the laboratory is that it's in a controlled manner, and we can study it in much more detail, and we don't have to wait and be lucky to catch a collision of neutron stars like we do for gravitational waves. And I showed you one observation of neutron star merger with electromagnetic counterpart, and unfortunately, this is still the only observation like this. So as far as I know, I think there is one other observation of two neutron star mergers, but as far as I'm aware, the electromagnetic part was not caught for this. And there are, of course, quite several already observations of mergers of black holes or a merger of black hole plus neutron star. But still, you understand that if we are relying on these observations, we just have to be lucky and catch one. While in the laboratory, we can do it in a controlled manner. On the right-hand side, a similar comparison also done for the entropy in such interactions. And again, you can see that the scale of this value is actually quite similar between objects of the mass of a sun and the object of a mass of a single nucleus. So we have so this oh, sorry, I think I just jumped to a different slide too fast. So as I said, we are actually have few decades of experience in studying this heavy ion collisions, and this was done in STAR, this was done in ALICE, and is being done actually in STAR and ALICE, also at low energies at SPS and NA61 experiment. But the most recent one that is being worked on right now is first of all CBM, and in the FAIR facility, and you can already see that the energy range for this experiment is exactly where we expect to produce matter, very similar in parameters to the Kisiel matter in neutron stars. And the CBM experiment very explicitly says that the goal is to study the phase structure and large biochemical potentials, effects of chiral symmetry, equation of state and density, and then they very explicitly say, as it is expected to occur in the core of neutron stars, right? And the other project that I've been heavily involved in is the project of NICA Accelerator and the MPD experiment. This is the facility constructed in the Laboratory of Energy Physics of the Joint Institute for Nuclear Research in Dubna. And this facility is being constructed already for several years, as well as the MPD experiment. And this was actually conducted as an international collaboration of more than 40 institutions from 13 countries. However, I must stress that as of last year, several institutions have withdrawn both from the MPD collaboration and from the Joint Institute for Nuclear Research, and that includes also my institution. So several institutions from Poland and Czech Republic and Bulgaria has actually left the collaboration. So what I'll be showing you is basically a status of the collaboration as of more or less this time last year. And the way that the work was organized in this collaboration was, first of all, we were organizing around the construction of the actual detector. And this is a collider detector at NICA. So this detector is expected to have just regular collider geometry. So in the middle, silicon detector for precise tracking, then the time projection chamber for more, let's say, comprehensive tracking, and then time of flight for particle identification, electromagnetic calorimeter for, again, particle identification, and also some studies of dilepton signatures. And then there are some additional detectors in the forward region, which characterize the collision and characterize and allow us to get centrality and the reaction plane. And in terms of physics, the work in this experiment was organized into so-called physics working groups. There were 5 defined for this analysis: global observable spectra and light fiber nuclei, correlations and fluctuations, electromagnetic probes, and heavy flavor. And these were the main physical avenues that the MPD collaboration is pursuing. And as I said, I left the collaboration more or less around the time where we were actually able to publish the summary of MPD physics and detector preparation, called the Status and Initial Physics Performance Studies of the MPD Experiment at NICA. This was published in the European Physical Journal. It really shows the very comprehensive review of the status of detector preparation and the status of the physics analysis that we're expecting to perform an MPD as of, let's say, middle of 2022. So if you're interested in more details, I strongly encourage you to look at this publication. And things that we're thinking about in terms of this study is, of course, first of all, to try to see whether at NICA energies we observe any kind of evidence for deconfinement. This, as I showed you, is already still an open question when we are talking about neutron star structure, or maybe not neutron star structure, but more about neutron star mergers, whether there's any chance of actually achieving deconfinement in such events. And of course, we know that deconfinement exists and occurs at high temperatures, low barochemical potentials, and there is even a more or less well-established estimate of the critical temperature where this occurs. And in heavy ion collisions at low energies, we of course do not reach that limit. We usually do not expect to cross this temperature of 160 MeV, which is been proven to be the deconfinement temperature at LHC, for example, or top peak energies. However, there is reason to believe that this deconfinement may happen at lower temperatures as long as the baryon density is high enough, and that's exactly the type of conditions that happen at low energy collisions, at like FAIR or NICA energies. There are some signatures that we might be looking for in order to determine whether such deconfinement occurs, and one of them is, for example, strangeness production. There are famous plots from SPS that argue that the specific patterns of strangeness production as a function of energy are indicative or of actually deconfinement at these energies, and you can actually see that there this so-called horn structure of the Na61 actually happens exactly in the range of energies obtained by or achieved in the NICA complex. But this study is definitely requiring a more detailed study, and it would certainly benefit with high statistics and also collider geometry studies in this energy range. Very similarly and extremely interestingly is the study of hypernuclei. Hypernucleus is extremely useful for all the topics that we discussed because, for example, it's an object where strange matter exists within regular nuclear matter. So exactly the question that we are trying to answer, what happens then? And then if we look at some theoretical calculations, they actually predict that the production of hypernuclei will be maximum at NICA energies, which is a bit counterintuitive. You would think that they are produced more in high energetic collisions, but that's actually not the case, because in high energetic collisions, the energy goes mostly into production of pions, while for the creation of hypernuclei, we actually need the production of nucleons, and that is actually maximum at around NICA energies. So that's another interesting avenue of research that could be pursued there. But what want to talk about in the let's say the second part of my talk is something that I personally worked on already for several years, and that is the study of the interaction of baryons. And as I said, one can imagine that the heavy ion collision, especially a high energy heavy ion collision, is more or less a factory of baryons and antibaryons. And all baryons and antibaryons, including very exotic ones, up to omega baryons, they are produced in rather large abundances in such collisions. And they actually, when they are produced, after they hadronize, they actually interact. And this interaction leaves an imprint on the produced particles in the way of two-particle correlations, and that is something that we would like to study. And such correlations, such correlations are the technique to study such correlations is called femtoscopy, and normally what is done in this, or sometimes HBT, what is done in such interactions is the measurement of the correlation function as a function of relative momentum of two particles, and this correlation function is related to the emission function, so what is the size of our source, and the interaction between these two particles. And in normal traditional HBT or femtoscopy, what is done is that this is usually done for pions, and then we know how the interaction looks like, and we try to determine what is the source function, or more modestly, what is the size of the source that's emitting these particles. But for baryons, we actually a little bit invert this question, and we say, well, we already measured our source function in a quite detailed way with pions, because they are, of course, most abundant. So let's say we would say we know what the source function is, and we can actually start asking questions about the interaction itself. And it turns out that the strength of the interaction will determine the shape of our correlation function. And if we know the source, then we can try to infer something about the interaction itself. This interaction, especially if you're talking about the strong interaction, can be expressed in a rather standard textbook way in the so-called effective range approximation. And if we remember this textbook, quantum mechanics, we actually have two parameters here about the interaction, so-called scattering length, which can be complex, and effective range, which can also be complex. And these are actually the parameters that parameterize the interaction, the strong interaction between these two particles. And this is something that we really want to know. For example, what would be extremely interesting for neutron star calculations would be to know the values of these parameters, for example, for lambdas and neutrons, or lambdas and psis, or neutrons and psis, and so on. And it turns out that when we include this interaction into our formula, we can actually perform this analysis, this integral in an analytical way, and we obtain the so-called Leditsky-Lubositz formula, which is a formula for a correlation function. So this formula is just fitted directly to our measurement. The correlation function is our measurement. We fit it directly, and we actually extract from it parameters of the interaction, scattering length and effective range. You can see they actually appear explicitly in the formula. So we just fit it, and we actually get these values. So we are, of course, there is slight complication here. We actually have to assume that we know the radius, because we cannot really fit the two of them independently. But once let's say we say we know the radius, we know it from other measurements, and also from quite robust modeling of the interaction, we are actually able to extract the values of the parameters of the interaction. And how do they appear in a correlation function? Well, if we have a negative real part, it will give us a negative correlation function, which is quite narrow in so-called relative momentum between the particles. But if we add the imaginary part, which is the annihilation, which appears in the formula for baryons and anti-baryons, we actually also get a negative correlation, but with quite wide feature in the relative momentum. So this is in principle showing us that the correlation function is not only sensitive to the scattering length, but also it is sensitive in a different way to different components of this scattering length. So we really have hope to be able to constrain those scattering lengths in a quite, let's say, detailed way. And this has been attempted already in STAR in 2005, 2006. They measured proton lambda, proton anti-lambda correlation. However, they observed something very, very striking and very puzzling, where they tried to do this analysis both for baryon-baryon and baryon anti-baryon pairs. So here you have proton lambda and antiproton anti-lambda. And then a second measurement of antiproton lambda and proton anti-lambda. When they extracted the radius from this measurement, it turned out that the radius for anti-pairs was a factor of 2 smaller, which was extremely unexpected and very, very difficult to explain, and and definitely not expected. So no model would predict any kind of difference of a size like that. And then this issue has been reanalyzed and thought in a bit more detailed way. And it turned out that especially for baryon-anti-baryon pairs, what we actually see is a significant contribution to the correlation function from the correlation of pairs that actually decay either into protons or lambdas. And that's something called residual correlations. So we actually have originally produced, for example, sigma and omega baryons, and then they correlate with themselves, and then much later decay, and they appear in our experiment as the decay products. So we may be fooled into thinking that they were original protons or lambdas, when in fact, these protons or lambdas are actually coming from a decay, and the correlation actually happened for the parent baryons, not for the baryons that we have measured. And this turned out to be an important factor, especially for baryon-antibaryon correlations. And it turned out that once we include this into our considerations, the discrepancy disappears. Basically, we are seeing a consistent system size for both particles. But what that tells us is that in the experiment, you expect to actually measure protons. Basically, they are directly observable in our detector, and maybe lambdas, okay? Through their decay products and V0 reconstruction, you expect to see lambdas. So if you talk about correlations that we are actually measure explicitly, it will be proton-proton, proton-lambda, and lambda-lambda. But all of those pairs are actually fed by decays of other types of pairs, and all of those pairs will actually influence the correlations that we have. You might think it's a problem because it becomes much more complicated to interpret such correlation functions, and it is, of course. But at the same time, you can actually look at it as an opportunity, because it turns out that, for example, interaction of two psi baryons is still influencing in a measurable way the correlation functions that we can access. In other words, it's accessible experimentally. So we can actually also use these residual correlations as a way to probe the interactions of particles that we are not able to measure even in heavy-ion collisions. And of course, you can imagine that any of those exotic pairs are completely impossible to measure in any other way, for example, in dedicated scattering experiments. So this shows quite a lot of promise in measuring quite exotic correlations and interaction parameters for exotic pairs. And this is an example of such study which is done by Alice. This is a measurement of baryon-anti-baryon annihilation, something that, again, has never been studied experimentally before, except for proton-anti-proton. So, for example, proton-anti-lambda or lambda-anti-lambda was never studied, and there was just some theoretical assumptions of what might happen. And Alice actually performed a measurement and extracted the parameters of the interaction for those pairs with the precision that's, of course, I mean, it's not unprecedented. Basically, no other experiment measured this, and it was the precision, experimental precision of this measurement was actually comparable to the precision of theoretical predictions. And what we found, for example, which was a little bit surprising, was that the annihilation parameters for all pairs, regardless of the quark content of the baryons, was quite similar. And that is not necessarily obvious. And for example, that is not what is assumed in UR-QMD, where this interaction is actually, this annihilation is expected to be a bit lower for heavier particles or particles which do not have exactly matching quark-anti-quark content. So in principle, this was, first of all, a unique measurement, and second of all, a measurement that not necessarily confirmed the previous theoretical predictions or assumptions. But Alice has been continuing this measurement also for baryons and also for proton-proton collisions, in which the system that we measure is a bit smaller. So we're actually sensitive to slightly different regions of the potential between the two baryons. And again, here we have, I would say, quite impressive results, measurements for proton-proton, proton-lambda, lambda-lambda pairs. Again, most of them are really unique in the world. There are some data from proton-lambda correlations, but they are quite scarce and not really that precise because they were taken a long time ago and suffer with slower statistics. For lambda, we have some indirect inference from the double lambda hypernuclei, but no measurement, no direct measurement of lambda correlations. And similarly, this is even more impressive. Alice has been able to measure proton Xi correlations, and also not shown on this plot, proton omega. So really, we are probing very much in detail the interaction between baryons, including strangeness. That again comes back directly to the topic I've been discussing, and the real motivation of those measurements is really to provide crucial constraints on these interaction parameters for models of neutron star matter or neutron star mergers. And this is very much a topic pursued by Alice. This is very much a topic that is one of the central pieces of the so-called Run-3 plan for Alice. And this is definitely a topic that could be very interesting in lower energy collisions. Why? Because at lower energies, of course, the relative multiplicity of baryons is high compared to heavy ion collisions. In Alice, baryons are rare. We are dominated by pions. So we have to struggle a little bit to extract those baryon-baryon correlations, while in lower energy collisions, we would actually be dominated by baryons, and it might be actually a bit easier to access those correlations, while the probing of the same interaction parameters is still possible. So in summary, I hope I showed you that heavy-ion collisions are exploring the QCD matter which have many parallels to astrophysics, including many interesting topics connected to neutron stars. We have a unique opportunity to study nuclear matter at large densities in the laboratory, and collisions at lower energies open up new research opportunities which are directly related to astrophysics. And I showed you some example of such studies where we can actually probe the interaction between exotic baryons in a way that is not accessible in the laboratory in any other way, and again has direct relevance to our neutron star questions. And these possibilities to measure the interaction is already heavily explored in star analysis, and have, I would say, a large potential in lower energy collisions such as CBM FAIR and other facilities. So thank you very much. Hello, I don't hear anybody. Somebody speaking. But...
Hello.
Hello. Yes.
Yes. So yeah, you can you see the in the chat box,
Yes, so the question is it possible to measure lambda D? By D, I hope you mean the D meson, right? No? So, in fact, the D meson, so first of all, it is already being pursued, the measurement of correlations of D meson with a pion, okay? That's already a challenging measurement, mostly because of the multiplicity of D mesons, right? But already now, deuteron lambda, that's also, okay. So deuteron lambda, again, this is, I would say, very much in the site. Currently, what is being worked on, and this is actually being worked on specifically by my group and some of my PhD students and collaborators. So first of all, we want to master the correlations with deuterons. And again, we start with particles that are most abundant. This is pion deuteron, and these results are more or less done. The next stage is to do kaon deuteron. This is interesting because that will already be an interaction of strangeness with deuteron, and that already is going to tell us something a little bit about the interaction, because of course all I've been saying was correlation with protons, while for neutron stars what we really want is the correlations with neutrons, and then deuterons is a way to actually a little bit go in this direction, because if we measure proton correlations and neutron correlations, we can sort of say, well, in deuterons, there is a combination of proton and neutron correlations. If we know the proton correlations and we know the neutron correlations, we can infer something about the neutron correlation. So we are already doing pion deuteron and kaon deuteron. Proton deuteron is definitely something that is our main goal right now. But if the proton deuteron is possible, I see no reason why lambda deuteron would not be possible, although it's slightly lower statistics, so it's maybe slightly later, but it's definitely possible. And we already see that it's possible to do pion deuteron and kaon deuteron correlations. Proton deuteron should also be doable, then lambda deuteron also, but but with a caveat that this really requires statistics of LHC run 3, which we have not yet taken. So run 3, as maybe you know, was started last year, but the heavy ion run was canceled last year. So we don't yet have heavy ion data from run 3 of LHC. We hope to get the first data this year, but the real luminosity will be delivered maybe in 2 years and 3 years. So this is definitely in the works, but we don't yet have the experimental data on tape to really do it in a, let's say, reasonable way.
Yeah, thank you, Adam. Thank you very much for your information, valuable information. Thank you.
Yeah.
Hello, Professor. May I ask a question?
Yes. Yes.
Yeah, I'm wondering, comparing with baryon-baryon interaction, what is it more difficult or easier to study a baryon-anti-baryon interaction within ALICE experiment? So
it really comes down to statistics, and actually at LHC the statistics is the same, so it's actually quite almost the same. I would even say that it's a bit easier to study baryon-antibaryon, just because so one positive is that the correlations for baryon and antibaryon is wider because of the annihilation. The annihilation produces a wider signal, so it's maybe more easy to see it. On the other hand, we actually have to be very, very, very careful about residual correlations, which are less important for baryon-baryon. So I would say it's not significantly more difficult. However, of course, at low energies, when the multiplicities of antibaryons is much, much smaller, it will be much more difficult. At LHC, it's comparable.
I see. Okay, thank you.
Yeah, so
any further question or? Not very clearly. Can you speak a bit louder or closer
maybe
to the microphone?
You can also put the question in chat, and then it will.
So how about now?
It's slightly better.
Yes. So in your slides, you say that the Kisiel and proton interaction will be possible, right?
Mm-hmm. Yes. So Kisiel. Maybe I will show the slides again. Cyan proton is already measured for baryon-baryon for proton-proton collisions, right? So this is let's say the measurement, right? So this is actual proton Psi experimental correlation function. Oh, it's actually PLED. So this is measured. So of course, the interpretation of it is so far just an indication of positive or attractive interaction, and we did not really extract parameters per se with error bars, but it's already much more than it was known. I mean, before it was simply not even known if the interaction is attractive or repulsive, right? And we already have data indicating that it's attractive, and again, this is from run 2 of LHC, and run 3 is expected to provide significantly higher statistics, and that should allow us to do a much more detailed study here.
So what you mean is in a condensed nuclear matter, the interaction is repulsive, but in a normal nuclear matter, so which is still the attractive, right?
So that's a question. Of course, what we do in heavy ions with this femtoscopy technique is we measure them let's say in quotes, in vacuum, right? So they are more or less free. So that's the measurement. That's what we have. And then it's a little bit of theoretical extrapolation of what you believe is going to happen in a dense matter. So that's why it's, for example, extremely interesting to compare these results to results from hypernuclei. But it's still more than nothing, I would say.
Okay, thank you. It's clear.
Hello, may I ask a more detailed question about
Yes.
So I'm wondering, so the source radius determined from one hadron pairs can be used to another hadron pairs to study the interactions. So I'm wondering, different hadron pairs share the same source radius. Is it an assumption or it is true?
That's a very, very good question. So I would say there are two aspects of this question. So one is I think in heavy ion collisions, we actually do not assume that all pairs are produced with the same source. Actually, what we do is slightly different. We actually have hydrodynamic models that work extremely well in reproducing pion and kaon source data from standard femtoscopy. So instead of just using other pairs, we actually use these models that we know work extremely well for basically all mesons and also baryons, and then just ask these models what they would predict about the source. So, and this, I would say, in my opinion, is very robust. I mean, hydrodynamic modeling of, especially in soft physics, of heavy ion collisions at LHC and at RHIC is very robust, and I think we really trust the sizes that we get there. A slightly different question is about proton-proton collisions. Then, indeed, there is a little bit of assumption that these sources go as what is called an empty scaling. I would say it's a little bit less founded in a theoretical aspect. However, even rather large variations. I mean, this source cannot be like outrageous. I mean, we know it's around 1 Fermi. It can be 1.2, it can be 1.4, but there is no way that this will go up to 10 or something like that. So, in fact, it is of course included in the uncertainty of the extracted parameters, this assumption about the size. But again, here in proton-proton, we say, well, there's simply no way that the source can be significantly larger. And there is also really no theoretical evidence to think that the source will be, for example, smaller than the size of a proton. That would be very strange. So then, even though we don't have such good theoretical understanding of the source, we still think it's more or less well constrained, and we do include it in the systematic uncertainty. Yes.
I see. Thank you. Sorry, a follow-up. So is the hydrodynamic model is not applicable to proton-proton collision? Is that right?
That's a very, very big debate in the whole community, of course. So some people are actually very excited about applying hydrodynamic model in proton-proton collisions. So this is very much a question. So, I mean, okay, well, let me be clear. Definitely not the hydrodynamic model in the sense of what we use for heavy ion collisions. So definitely not the same. Whether some other version of hydrodynamic model could or should be used in proton-proton collisions with the underlying assumption that this hydrodynamic model especially is useful when there is deconfinement, that's actually the big question, okay? But that's not really what we are talking about here. But I would say, well, we actually have extremely precise data of pion femtoscopy in proton-proton collisions. And so far, I have not seen any model, hydrodynamic or non-hydrodynamic, that is able to reproduce all features of this data. This is very much different to heavy ions, where in heavy ions, hydrodynamic model just works. It works qualitatively, quantitatively. There is simply no question. We really understand what's happening. In proton-proton, I wouldn't say this is the case. There is really very much a lack of model that would really attempt to describe the space-time behavior of the source in a detailed way.
I see. I see. Yeah, thank you. Thank you for your comprehensive information.
Yeah, thank you.
Thanks. And further questions or discussions? Even this talk is, I mean, only focus on the Alice, but I think Adam doesn't mind to have a answer or have a quick discussion about the MPD or some other things. If you have those kind of question, also this is a very good opportunity. Please feel free to. Okay, so I hear nothing, and if no more, basically, Kaja, are you gonna say something?
Oh yeah, thank you. Oh, hi, Adam. I have another question. Yeah, on slide maybe 17, you compare the neutron star and heavy-ion collisions. You mentioned that the temperatures in these two systems are amazingly quite similar. I would want, I would want to know that whether the baryon number density are similar, and also in the neutron star merger, the isospin asymmetry, I think is much larger than that in the heavy-ion collisions, right?
Yeah,
right.
That's right. That's right. That's the main difference, I would say, between these two systems is the isospin symmetry. I think the density is quite similar, but the isospin asymmetry is, of course, quite different. So so obviously, as you're saying, we cannot directly compare them. But on the other hand, this is the only way that we can access any kind of matter with anything approximating this kind of conditions, right? So it's true that the isospin is not the same, but it's still much closer than anything else that we could produce in a controlled way in a laboratory. So I would say that anyway, we strongly rely on the models in order to tell us what's happening in a neutron star. So we are also forced here to rely a little bit of extrapolation from this isospin symmetric matter to neutron-rich matter. And that's life. That's what we can do. But I think it's still very interesting to see what is going on here. Yeah.
Yes, thank you. Yeah, I agree with you. Thank you very much for the explanation. Thank you.
Boqiang, are you? No, you. I see your microphone is on. Okay, so if no more question, basically we can conclude this seminar. We thank Adam very much again for this very nice presentation and the discussion. So
thank you very much.
Yeah. Hope to talk to you next time and maybe see you in person later this year.
Yes.
Okay. Then thanks also to everyone for attending today. So we conclude today's seminar. Bye-bye.
Thank you very much. Bye-bye.
Thank you very much. Bye-bye.